Good morning, everyone. Myself, Monica Mansupriya, Assistant Professor from the Department of Electrical and Electronics Engineering. And the subject I'm handling is basic Electrical and Electronics Engineering, the subject code W25C01 under the regulation 2025. In this session, we begin Unit 5, Digital Electronics. This unit introduces the basic ideas behind digital systems, number systems, logic levels, digital waveforms. So these are the foundation for understanding digital circuits used in computers, calculators, watches, and communication devices. So first, we are going into the circuits and logic gates. You must understand the digital electronics actually. So first, digital electronics. So this digital electronics is a branch of electronics in which information is represented using the discrete values, normally two levels, that is namely 0 and 1. Unlike the analog electronics where signals can take any values in the continuous range, digital electronics works with only fixed levels. So this digital systems is easier to design, more reliable and less affected by noise and suitable for computation and data processing. Second one is the key concept to emphasize was digital is equals to discrete and analog is equals to continuous. So digital systems usually use a binary representation. So to understand the digital electronic better, let us first look onto the common device around them for the digital system. First, the introduction of the digital electronics is the digital electronics is not just a theory topic. It is present in many devices. We usually daily use computers, calculators, digital watches, mobile phones, cameras, TV, control systems, and industrial controllers. So these devices process information in digital form, that means data inside them is represented using the digits 0 and 1. So in a calculator, numbers are entered, processed. In this diagram, analog input, we are taking a calculator. So we are typing number 3 plus 5 in analog input. Then it converts ADC, that is analog to digital converter. Using that, we are getting the information in the digital system in the form of zeros and one. So numbers are entered, processed digitally and displayed. In the computer, text, images, sound, instructions are all converted into the binary form and it processes it. So digital systems are preferred because they can store, process, and transmit information accurately. Even if there is a small disturbance or noise, the system can still distinguish between the logic 0 and logic 1. So, can you think of any device in your home that works digitally? This creates the interaction. So, let us move on for the examples of digital devices. These are the images related to digital electronics. This contain the pictures probably introducing the hardware to the digital blocks. Hardware to the digital block. This slide visually, even though a computer or calculator appears as one complete device externally, internally it contains semiconductor devices, switching circuits, logic gates, memory units, and processing blocks. So whenever we study digital electronics, we are really studying how these internal parts represent manipulate the binary information. So if the images are visible, refer to one by one and connect them to the digital application. The purpose of the slide is to show the digital systems are built from many interconnected parts. We are giving analog input 8, 5, but it transmits into digital form. That is 4-bit, 8421. So 8 means 1. 421, that is 0. Here we are having 5. So 8041 201. So 4 plus 1, 5. So it mentioned in the 5. So next one is the encoder decoder counters. So in encoder decoder counters, registers added in this digital system, we are having the subsystem. So first, the basic electronic system. We are having the digital circuits are physically built as the electronic components such as the resistors, capacitors. So among these transistors is most common in digital electronics. It acts like a electronic switch. So digital systems operate using on and off condition. The transistor is ideal for the implementing the logic. So transistor can act as a switch or amplifier. Resistor control the current and help to set the voltage level. Capacitor store the charge temporarily. Next one is the subsystem. It's the logic gates. And this logic gates having the AND gate, OR gate, NOT gate, NAND gate, NOR, XOR, XNOR. So these are the logic gates which are used. In module, we are using encoder, decoder, counters, registers, and adders. So in the functional block, we are having the adder, subtract, adder, encoder, decoder. These are all. So in translation, before studying these circuit in detail, we must understand how numbers are represented inside the digital system, and that brings us to the number system. So these are the basic informations, and the introduction of the number system is this. Defines in the decimal is base 10, and in the binary it represents base 2, and the octal means 8, so it's a base 8, and the hexadecimal is 16, so it's a base 16. So if we want to convert into decimal form, we having number in the base 10. If we want to convert, if this is a binary, if there is a number base 2. If you want to convert into the hexadecimal, this is a number and base 16. So a number system is a method of representing quantities using a set of symbols. In digital electronics, number systems are extremely important because computers and digital devices do not work directly with the decimal numbers. So the way the human usually do this number system base radius. So the decimal uses 10 symbols 0 to 9, and the binary uses 2 means 0 to 1. Octal uses 8 means 0 to 7, and the hexadecimal means 0 to 9 or A to F and A to F. A means 10, that is two-digit number 10. B means 11, C 12, D 13, E 14, and F is 15. So this digital circuits naturally understand the binary because they operate using two states. Then this is the decimal number system. In the decimal number system is the number system. We use the in everyday life. It has a base 10, which means it uses the 10 symbols. That is 0 to 9. So 10 means 0 to 9, totally 10. For example, we take the number 7392.91. Explain place value is from left to the decimal. From the left to the decimal, we are having this is 2 in the place of ones, 9 in the place of tens, 3 in the place of hundreds, and 7 in the place of thousands. So 2 in the place of ones, so 2 into 10 power 0, and tens place 2 into 10, 3 into 100, 7 into 1000. So these only we write from after the decimal point, we are going from right to left. That is 9 in the place of 9. 7392.91 means, so in 9, 10 to the power of minus 1, 10 to the power of minus 2. So we have to write this in the format. Then the next one is a binary number system. And this binary number system has base 2 and is usually uses the two digits 0 and 1. So this is the most important number system in digital electronics because the digital circuit always easily represent the two conditions, on and off, that is high and low, 0 and 1. So these are the types. Each position in a binary number has a weight that the power of 2. Take the binary number 1001.101 means 1 in the place of ones, 0 tens, 0 hundreds, and 1 in the thousands. So these are the thing. And we are having the after the decimal point is 101 means 1 into the power of 2 power of minus 1, 0 to power of minus 2, and 1 to power of minus 1. So bit, that is a binary digit. A group of 4 bit is a nibble, and the group of 8 bit is a byte. So this is the binary is used, and octal is also the same in the place of 8, octal 8. The number having the base 8, ones, tens, 100, 1000 in terms of 8. So 5 into 8 power 3 plus 6 into 8 power 2 plus 3 into 8 power 1 and 2 into 8 power 0. After the decimal point is also 8 power minus 1, 8 power minus 2, 8 power minus. This is the one. And the hexadecimal is also having the same one, having 16, so 0 to F, and 3 FD. So 3 D into 16 power 0, F into 16 power 1, and 3 into 16 power 2. And after the decimal point, 16 power minus 1 and 16 power minus 2. And the binary digits and logic levels is this is the digital electronics uses a circuit are physically represented by the voltage level. So a circuit does not understand the symbol 0 or 1 or by itself. Instead, one voltage range is treated as low, another voltage range is treated as high. So they correspond to the logic 0 is low and the logic 1 is high. So when we say a digital circuit stores or transmits a binary value, we actually mean it maintains a certain voltage level. So 0 volt may represent the logic 0 and 5 volt may represent the logic 1. So if the voltage levels change over time, they form digital signals or digital waveform. Let us study the next one. And the digital waveform is a graphical representation of how the digital signal changes with time. Since the digital signals have only two logic levels, the waveform switches between low level and high level. So these changes are not gradual in ideal digital system, and they are considered abrupt transmission. So the pulse, what is mean the pulse? A pulse is the temporary change in the logic level. So for example, if a signal normally stays low, then rises to a high for a short duration, then it returns to low. So this is called the positive going pulse. And for the high to low to high, it's a negative pulse, and low to high to low is the positive pulse. So the rising edge, this is the rising edge from low to high, is the transition from low to high. And the falling edge is transition from high to low. And the pulse width is duration of which pulse remains high. And the time period is total time of one cycle. And the frequency is the number of cycles per second. For a second, how many cycles are formed? That is the frequency. So these are the digital waveforms. In this session, we have studied the basics of digital electronics and what are the number systems in the digital electronics. We have discussed about decimal, binary, hexadecimal, octal. We have discussed about the logic gates also, and we have studied about the digital waveforms also. These are the references. We will see you in the next topic. Thank you.